Well, yesterday we saw some basic definitions of Riemann integrals as well as Riemann-Stieltjes integrals, namely upper sums, lower sums, what is meant by lower Riemann integral or lower Riemann-Stieltjes integral, similarly upper Riemann integral as well as Riemann-Stieltjes integral, and we have seen that we say that the function is Riemann integrable if the upper Riemann integral coincides with the lower Riemann integral, similarly in case of Riemann-Stieltjes integral. And then we have seen that using this definition we can decide about the integrability or otherwise of very few functions, and so we need some good criteria to decide whether a function is integrable or not. And in order to come up with some useful results of that type, we started discussing what is meant by refinement of a partition and what happens to lower and upper sums when you consider refinement. So let us recall that last result. So what we had seen was that suppose we take P star is a refinement of P, okay, and see P and P star both are partitions, okay, P and P star both are and that means P star contains all the points of P plus possibly a few more, okay. And we have seen that in this case what happens is that lower sum of this lower sum will increase and upper sum will decrease, right. So what we know is that LPF is less than or equal to LP star F and UPF is bigger than or equal to UP star F, okay, right, okay. Now this has a very important consequence, namely using this we can prove that every lower sum is less than or equal to every upper sum. See, till now what we know is, okay, not only this, in fact we have proved something, this is for the Riemann sums, but we have also proved it for Riemann-Stieltjes sums, right, okay. See, what we know for any partition, let me again recall that we have shown that for any partition this LPF alpha is less than or equal to, let us say, this Stieltjes sum SPF alpha, this is less than or equal to UPF alpha, and okay, let me recall that also, this will be less than or equal to big M times alpha b minus alpha a, and this will be bigger than or equal to small m times alpha b minus alpha a, okay. But using this what we can show is that if you take any two partitions, then lower sum with respect to any partition is less than or equal to upper sum with respect to every partition, okay, and that will enable us to prove that the lower integral is always less than or equal to the upper integral, okay, that is our idea. So let us just take in the same way, suppose let P and Q be two partitions, okay, let P and Q be two partitions, okay. Then look at P union Q, okay. P union Q is a refinement of both, right, P union Q is a refinement of P as well as refinement of Q, right. So that P union Q is a refinement of both P and Q, okay. So we can apply these results, okay. So lower sum of P union Q will be bigger than or equal to lower sum of P, okay. So we can say that hence lower sum of P union Q, sorry, I want the other way, okay, that is lower sum of P, that's right, is less than or equal to lower sum of P union Q, right, okay, because P union Q is a refinement, okay, and lower sum of P union Q will obviously less than or equal to upper sum of P union Q, okay. Okay, let us use this notation. Of course, actually when F and alpha are fixed for the discussion, we can simply say LP and UP etc., but anyway let us be more precise. Okay, so then LP F alpha is less than or equal to L P union Q F alpha, and we know that for any partition lower sum is less than or equal to upper sum of that partition. So this is something we have already seen there. So less than or equal to U of P union Q F alpha, and now we use the fact that P union Q is also a refinement of Q. Okay, so the upper sum of P union Q must be less than or equal to upper sum of Q with respect. So this means this is less than or equal to Q F upper sum of Q, right. So what did we prove? That lower sum with respect to if you take any two partitions P and Q, lower sum with respect to any partition is less than or equal to upper sum with respect to any other partition. That means all lower sums are not only that a lower sum of a particular partition is less than or equal to the upper sum of that particular partition, but all lower sums are less than or equal to all upper sums. Okay, right. Okay, but now let us recall the definition of upper and lower integrals. Okay, what was this upper integral? Integral a to b f d alpha. Okay, with one line here. This was infimum of u p f alpha, infimum taken over R. Okay, right. And similarly lower integral was supremum of all lower sums. Okay, okay, just to avoid confusion, let me use some other letter here. Okay, it's a, let us say it is supremum of LQF for Q in the partition P, LQF alpha. Okay, so now what we can say is that, let us say you fix a partition Q here. Okay, take some partition Q from here, then you can say that LQF alpha is less than or equal to U P F alpha for every P, right. Okay. So suppose you take a particular partition Q here, then the lower sum with respect to that partition is less than or equal to every upper sum. Okay, which means this is a lower bound. Okay, and if it is a lower bound and this is a greatest lower bound, infimum is the greatest lower bound, so any lower bound must be less than or equal to infimum. So that means, so this implies that LQF alpha is less than or equal to this infimum of UPF alpha for P in P, and this is nothing but the upper integral. Okay, okay, right. Okay, so what did we prove? That if you take any partition Q, then its lower sum is less than or equal to the upper integral. Okay, its lower sum is less than or equal to upper integral. Now what we can say is that this is true for every Q. Okay, this is because there was no particular property of Q that we have just taken any arbitrary partition and fixed. So every lower sum is less than or equal to this number. That means this number is an upper bound of this set. Okay, this number is an upper bound of this set, and this upper integral is the least upper bound. Okay, least, so that least upper bound must be less than or equal to any upper bound. Okay, right. So that shows that since this holds for every Q in, since this holds for all partition Q, this holds for every Q in this set of all partition P. Okay, we get supremum of this must be less than or equal to this number, or which is same as saying that the lower integral a to b f d alpha is less than or equal to upper integral a to b f d alpha. Okay, So remember, to take the stock of whatever we have done so far, we have proved that once a bounded function is given, the upper integral and lower integrals will always exist, okay, and we say that the function is integrable if these two numbers coincide, okay. And what is the extra thing that we proved now is that the lower integral is always less than or equal to the upper integral, okay. So to show that a function is integrable, what is required to show now? We must show that upper integral is less than or equal to the lower integral, okay. If that, because this inequality always holds, this always holds, okay. So to show that a function is integrable, we must show that this upper integral is less than or equal to lower integral, okay. And to do this also, we use a very standard technique in analysis which is used very often, okay. For example, when you want to show that one number is less than or equal to the other, and suppose you cannot do it directly easily, then you, for example, suppose you wanted to show that alpha is less than or equal to beta, okay, and you can't do it easily directly, then you show that alpha is less than or equal to beta plus epsilon for every epsilon, okay. Then that will follow for every positive epsilon, then from that it will follow that alpha is less than or equal to beta. This is a very standard technique used in proving inequalities of this type, okay. You would have come across this kind of proofs fairly often, okay. So that is what we do, and taking this into account, now we will give a relatively easy criteria to decide whether a function is integrable or not, and then we shall use that criteria to show that several functions that we come across in practice are integrable, okay. So what is that criteria? It is, okay, let us state that as a theorem, okay. Okay, that is a theorem, okay. So as usual, let f from AB to R be bounded, okay. Then we say that f is integrable, okay. We can prove it first tilde integral also directly instead of just proving for Riemann integral. Let f be bounded and alpha from AB to R be monotonically increasing, okay. Then f is integrable, that is, okay, let us use this notation. F is, we had said f is, okay, or fine, f is Riemann-Stieltjes integrable if and only if what should happen is that for every epsilon bigger than 0, suppose you are given some epsilon, for every epsilon bigger than 0, you should be able to find a partition such that the difference between the upper and lower sum of that partition should be less than epsilon, okay. If that can be done, then function is Riemann-Stieltjes integrable, okay. For every epsilon bigger than 0, there exists a partition P such that, of course, upper sum is going to be always bigger than or equal to the lower sum, okay. So we can simply say such that U P F alpha minus L P F alpha is less than epsilon, okay. That means all that we need to do is that given any epsilon, we should find a partition P such that for that partition P the difference between upper and lower sum is less than epsilon. Suppose you do that, then that is enough, that's enough to conclude that the function is Riemann integrable, okay. Riemann or Riemann-Stieltjes integrable, in this, depending on which kinds of sums you take, it will be Riemann integrable or Riemann-Stieltjes integrable, okay. And in proving this, we shall make use of the observation which I made just now, namely that whenever you want to show that alpha is less than or equal to beta, you try to show that alpha is less than equal to beta plus epsilon for every epsilon, okay. That is what we shall use, and for that we note the following. See, remember, we have already shown that every lower sum is less than or equal to the, in fact every upper sum is less than, okay, let me just again recall that observation, because upper integral is the infimum of the upper sum, okay, infimum of the upper sums. So this will be always true, that is you can say that for every partition P, okay, this is something that we know always, LP F alpha, okay, in fact okay, let me write it like this, okay, you can always say this, that integral a to b f d alpha, there is upper integral, this is less than or equal to up f alpha, right, that is always true, right, because this is an infimum of sums of this type, so in particular it is a lower bound, okay, and now we have proved that upper integral is always bigger than or equal to the lower integral, okay, right, and is it also clear that lower integral will be always bigger than or equal to the lower, any lower sum, okay, because lower integral is the supremum of all the lower sums, okay, all right, okay. Now after this observation, does the proof of this part becomes obvious? Suppose we know that given any partition, given any epsilon, there exists a partition P, okay, such that the difference between upper and lower sum is less than epsilon. If the difference between upper, that is, see, if the difference between these two is less than epsilon, then these two numbers are lying in between those two, so the difference between these two also must be less than or equal to epsilon, okay, right. So what is the proof here? This is true, okay, this is true for every P. Let us now look at the, we are assuming this, that for every epsilon bigger than 0 there exists a partition P, etc., and using that we are showing this. So that means we are proving this part, okay, we are proving this part, okay. So let epsilon be bigger than 0 and P belonging to P be such that UPF alpha minus LPF alpha is less than epsilon, okay, okay, right. So does it follow from there that difference between upper integral and lower integral is also less than epsilon, okay, that is then integral a to b f d alpha minus the lower integral is less than epsilon, okay, all right. Or this same inequality I can write in a slightly different way. Instead of writing that this minus this is less than epsilon, I shall say that this is less than this plus epsilon, okay, that is the same thing, right, okay, and that is what we wanted to prove, that for every epsilon this number upper integral is less than lower integral plus epsilon, so upper integral must be less than or equal to, okay, so since this holds for every epsilon, for every epsilon bigger than 0 we have, okay, we have this integral upper integral is less than or equal to the lower integral, okay. That completes the proof of this part, okay, that completes the proof of this part, okay. Okay, so now we will show this part, okay. This part means what? Suppose f is Riemann-Stieltjes integrable, okay, then given epsilon there should exist a partition P such that this happens, okay. So suppose f is Riemann-Stieltjes integrable, what does this mean? It by definition this means that the lower integral is same as the upper integral, okay, that is this lower integral a to b f d alpha, this is same as the upper integral a to b f d alpha. Okay. All right. And what we have to show is that if this is the case, then for every epsilon we can find a partition P with that property. So let us start with this. Okay, so let epsilon be bigger than 0. Okay, let epsilon be bigger than 0. Okay. Now here it will also help to recall the definitions of this. Okay, what is this? Again, let us recall. This is nothing but the infimum of the upper sum. Right. P belongs to script P, and this is nothing but the supremum of the lower sums. Again, the way in which infimum and supremum are used in most of the proofs is as follows. In fact, this is also something you would have come across very often. Okay. What is the meaning of infimum? Infimum is the greatest lower bound, right? Infimum is the greatest lower bound. If it is the greatest lower bound, if you take any number bigger than that, then that is not a lower bound. Okay, if you take any number. Now if something is not a lower bound means what? There should exist some number in that set which is strictly less than that number. Okay. So for example, okay, now we are given this epsilon bigger than 0. Suppose I take something like this plus epsilon or this plus epsilon by 2, then that is not a lower bound. So there should exist a partition here such that the corresponding sum of that partition should be less than this plus epsilon by 2, right? Okay. So one can say that there exists a partition. Suppose I call it partition P1. There exists a partition P1 in script P such that what should happen? U P1 F alpha should be strictly less than this upper integral a to b f d alpha plus epsilon by 2. Okay. Do you agree? Okay, all right. Is it clear? Because if all of these were bigger than or equal to this would have become a lower bound. That is not the case, right? Okay. Use the same thing here. What is the supremum? Supremum is the least upper bound. Okay, supremum is the least upper bound. So that means if you take any number smaller than that, that is not an upper bound. Okay, that means there should exist something here which is bigger than that number. Okay, right. So we can say that similarly there exists P1, sorry not P2 in script P such that what should happen? LP F alpha should be bigger than, because this integral lower integral, oh sorry, this should have been the upper integral here. Okay, because we have used this part. Okay. This should have been the upper. So this lower sum is less than the lower integral minus epsilon by 2. This is P2. So if you had, so what is our aim actually? We want to find a partition P such that for that partition P, U P F alpha minus L P F alpha is less than epsilon. Okay. Suppose this P1 and P2 were the same. If P1 and P2 were the same, then we could have simply said that this is less than this plus epsilon by 2, this is bigger than this minus epsilon by 2, and these two are the same actually. That is our starting assumption, right? Okay. So suppose you call this common number as sub number I, that is the integral, or okay, that is in fact that is what we have called integral a to b f d alpha, right? This common value is what we call integral a to b f d alpha, right? So I can forget about these symbols now. Okay. So this upper sum is less than this number plus epsilon by 2, this lower sum is bigger than this number minus epsilon by 2. So suppose we subtract, you will get, because when you subtract this inequality will be reversed, this will be cancelled. Okay, and you will get u, if P1 and P2 were same, you would have got U P F alpha minus L P F alpha is less than epsilon, which is what we required. Okay, but that is not the case. Okay, in general, because we have obtained P1 and P2 from these definitions, So in general they will be different, okay, in general they will be different, but again now it is obvious what is to be done in such a case. Yeah, take the refinement, that is take the union, okay, and that will satisfy both these inequalities, okay. So let P be equal to P1 union P2, then P is a refinement of both, okay. Then since P is a refinement, of both P1 as well as P2, what we will get is that okay, I think I will continue there. Okay. What we will get is U P F alpha, this is less than or equal to U, since P is a refinement of P1, upper sum with respect to P is less than or equal to this, okay. So U P1 this is less than or equal to U P1 F alpha, and this is less than integral A to B F d alpha plus epsilon by 2, okay, and L P F alpha is bigger than or equal to L P2 F alpha, okay, because lower sums increase, okay. This is P comma F comma alpha, okay. So this is bigger than integral A to B F d alpha minus epsilon by 2, okay, and this implies that this means U P F alpha minus L P F alpha is less than epsilon, okay, and this completes the proof, okay. So what we have shown is that if f is Riemann-Stieltjes integrable given any epsilon, we can find a partition P such that for that partition U P F alpha minus L P F alpha is less than epsilon, okay. And other way we have shown earlier that if this property is true, then the function is Riemann integrable, okay? Riemann-Stieltjes integrable, okay. All right. So now, as I said in the beginning, this is a very useful criteria, and this helps us in deciding that about fairly large classes of functions are integrable. So the first such important class is that of continuous functions, okay. This will help us show that every continuous function is Riemann-Stieltjes integrable, and so that takes care of a fairly big class, okay, that takes care of a fairly big class. So once you know that the function is continuous, then you can immediately say that it is integrable, okay. So okay, if okay, I think I will write it here itself, okay. Because these assumptions are standard for whatever we want go into proof, okay. So what is the additional thing that we require, that if f is also continuous, then f is Riemann integrable, Riemann-Stieltjes integrable. If f is continuous on AB, then okay, I think we shall first this for this theorem, it is better to prove it first for Riemann integrals rather than Riemann-Stieltjes integrals, okay. So I will remove this part, and in fact once we say it is continuous, we did not say it is bounded also, right, because it is a closed and bounded interval, okay. I think it is better to write a separate statement, okay. So in fact we can write it in a short form, okay, that is, you know, this class CAB, right. It is the set of all continuous functions defined on AB, continuous, let us say continuous real valued, okay, and then all that we want to say is that every continuous function is Riemann integrable. So CAB is contained in this RAB, or in words this means that every continuous function is Riemann integrable, okay. Every continuous function is Riemann integrable, okay. And for the proof, okay, for the proof we are going to use the previous theorem, okay. So the way in which we will prove is that given any epsilon we shall produce a partition such that for that partition the difference between upper and lower sum is less than epsilon, okay. And since we are talking about Riemann integral now, this alpha will not be there, it will just UPF minus LPF, okay. So let epsilon be bigger than 0, okay. Then what we can do is that we can think of some number for which okay, let me come to that little later, okay. Basically we are going to use the fact that this AB is a compact set, okay. So every continuous function on a compact set is uniformly continuous, of course it is bounded etc, that is all there, but it is also uniformly continuous, okay. It is also uniformly continuous, okay. So we can say that there exists delta bigger than 0 such that if you take any two points in AB whose difference is less than delta, okay, then the difference between Fx and Fy is less than epsilon, okay, is less than epsilon. There exists delta bigger than 0 such that for all xy in AB with mod x minus y less than delta, mod of Fx minus Fy is less than epsilon. This is because F is uniformly continuous on AB, okay, because this is because F is uniformly continuous. Okay. So here we are using the fact that a continuous function on a compact set is uniformly continuous, something that I suppose you have already done, okay. Continuous functions on a continuous function on a compact metric space is uniformly continuous, okay. Only thing is that, see, ultimately what we want is that UPF alpha minus LPF alpha, that should be less than epsilon, okay. So so here for the time being, instead of taking this epsilon, I shall take this epsilon 1, let us say. We shall choose this number epsilon 1 depending on this epsilon later, okay. Okay, because ultimately what we want is that the difference between upper and lower sum should be less than epsilon. So we shall choose epsilon after this epsilon 1 afterwards, okay. Now what we do is that we take a partition in such a way that the length of all the partitions is less than this delta, length of all the partitions is less than this delta. So for this I think it is better to introduce a notation here which may be useful subsequently also, okay. Okay, let me write it here. Suppose P is a partition, P is a, let us say P is a partition which is of this type: A is equal to x0 less than x1 etc etc less than xn equal to B, okay. Then we have said that we will call this delta xi to be xi minus xi minus 1, xi minus xi minus 1, okay, and that is the length of the ith subinterval, length of the ith subinterval. There are n such subintervals, okay. So you take the maximum of that, that is called mesh of the partition and denoted by mu of P, maximum of delta xi I going from 1 to n. So this is called mesh of P. Okay. All right. Now coming back to this proof, given an epsilon we have found a delta such that whenever mod x minus y is less than delta, mod fx minus fy is less than, okay, some number depending on epsilon, okay, that choice we will do later. Okay. So now what we do is that find a partition such that the mesh of that partition is less than delta. Okay. So consider a partition P such that mesh of the partition P is less than delta. Is it clear that such a partition can be chosen very easily? Okay. For example, one possibility is that I can take all these intervals are of the same length. Okay, I can take all these intervals of the same length. If that happens, then each of this delta xi will be b minus a by n. There are n such things. Okay, right? Okay, that is, you choose x naught equal to a, x1 is equal to a plus b minus a by n, then x2 is equal to a plus 2 times b minus a by n, etc. Then the length of each partition, each subinterval will be b minus a by n. Okay, then can we always choose n such that this b minus a by n is less than delta, right? Whatever the number delta is given, okay, b minus a by n tends to 0, so we can always choose n big enough such that b minus a by n is less than delta. Fine. So this is no problem. We can, given any delta, we can always choose a partition. We can always choose a partition such that the mesh of that partition is less than delta. That's clear. Okay. That is why we did not describe how it is to be chosen. Okay. So now what is going to happen is that suppose you take any x and y in the subinterval. Okay. Then for this partition, suppose x and y belong to this subinterval xi minus 1 to xi. Okay. Then since this length is less than delta, the difference between function values here, difference between fx and fy must be less than this epsilon. Okay. So this implies mod fx minus fy must be less than epsilon. Okay. Okay, epsilon 1, fine. Okay. Okay. Now what can we say about this quantity big mi minus small mi? Is it clear to you that big mi minus small mi is the biggest among the difference between fx and fy? See, big mi, what is big mi? Let us recall, big mi is the supremum of fx for x belonging to this xi minus 1 to xi, and small mi is infimum of the same thing. Okay. There is small mi is the smallest possible value that f can take, and big mi is the biggest. Remember, in this case this supremum I can say as the maximum also, because f is a continuous function. Okay. Because f is a continuous function, there will exist some point at which this maximum is occur. Similarly, there will exist some point at which this minimum will occur, and for any x and y, the difference between fx and fy must be less than or equal to this big mi minus small mi. Okay. But what we know is that for any x and y, that difference is less than epsilon 1. Okay. So suppose I choose say x for which fx becomes this big mi, and choose y such that fy becomes this small mi. Okay, then the difference between these two is less than epsilon. Okay, right. So what I can say, epsilon, let epsilon 1. Okay, then I can say that then big mi minus small mi is less than epsilon 1. Okay. All right. Now you look at UPF minus LPF. Okay. Is it clear that this is same as sigma I going from 1 to n, sigma I going from 1 to n, big mi minus small mi multiplied by delta xi, right, because UPF alpha is big mi into delta xi, LPF alpha is small mi into delta xi. So the difference will be given by this, but what we know is that this number is less than epsilon 1, this number is less than epsilon 1 for each I, so that so we can say that is less than sigma this epsilon 1 into delta xi, okay, but we know that sigma delta xi is b minus a, okay, so this will be less than epsilon 1 into b minus a, okay, right. And now come back to our idea, we wanted to find a partition such that this difference is less than epsilon, okay, this difference is less than epsilon, okay. So if I take this epsilon 1 as epsilon divided by b minus a, then this final thing will be less than epsilon, okay. So we can say that here okay, let epsilon be bigger than 0 and take epsilon 1 is equal to what, epsilon divided by b minus a, epsilon divided by b minus a, so that will also be bigger than 0 if epsilon is bigger than 0, etc. Okay. Okay, so suppose you take epsilon 1 as epsilon by b minus a, this is less than epsilon, okay, is it clear? So again let us recall, what did we do? We showed that given any epsilon we can find a partition P, such that for that partition UPF minus LPF is less than epsilon, okay, and we already said that if that happens the function must be Riemann integrable, okay, right, function must be, we did not show it for any arbitrary alpha, okay, we showed it for this, okay, if we could show this for any arbitrary alpha we could have said that the function is Riemann-Stieltjes integrable, okay. Now let me come to that, is this clear first of all, okay, now let me come to that problem, okay, when can we say that suppose a function is continuous, when can we say that it is Riemann-Stieltjes integrable, what will be the changes required here? See if you look at this difference, instead of UPF you will get UPF alpha minus LPF alpha, you will get UPF alpha minus LPF alpha, then that will be mi minus mi into delta alpha I, okay, delta alpha I is alpha xi minus alpha, so this will be less than epsilon 1 into alpha b minus alpha a, okay. Now what happens here is that we will need to choose a partition in such a way that this big mi minus, okay, so that is the only change, instead of taking epsilon 1 as epsilon divided by b minus a, okay, you will need to take epsilon divided by alpha b minus alpha a, that is all, okay. So let me come back to this what I started. So suppose f from AB to R is bounded and alpha from AB to R is monotonically increasing, then if f is continuous, then f is Riemann-Stieltjes integrable, okay. We did not discuss this proof separately because there is only one change here, namely that instead of taking epsilon 1 as epsilon divided by b minus a, you just take epsilon divided by alpha b minus alpha a, that is the only change, rest of the proof will remain as it is, okay. Now this tells us that, okay, let us come back to this theorem again. This tells us that every continuous function is Riemann integrable or Riemann-Stieltjes integrable depending on what you want. Okay. Now what happens if the function is not continuous at, let us say, one point? Okay. What happens if the function is not continuous at one point? Then what we can say is that you choose, suppose look at the point at which the function is discontinuous, suppose that is the point x naught. Okay. What you do is that you choose this particular interval containing x naught to be very small. Okay, you choose this particular interval containing x naught to be very small. So what will be the contribution due to this interval to let us say, basically what we want is that we want to make this UPF minus LPF to be very small. Okay, that is the idea. Okay. Now what will be the contribution to this UPF minus LPF? It will be this particular, suppose this is delta xi, suppose this is ith subinterval, then contribution to that from this will be mi minus mi divided by delta xi. Okay. Okay. Now what we can do is that for all other intervals we can make this mi minus small mi to be less than this epsilon by b minus a. Okay, for every other subinterval. We cannot do it for this particular subinterval. Okay, so what we do is that for this particular subinterval we will make this delta xi to be very small. Okay, over this we do not have control, but of course still we do not have control means we still know that it is, see, we can always say that this will be always less than or equal to big M minus small m, right. Okay, this will be always, and this into delta xi. Okay, so suppose I choose this delta xi so small, this delta xi so small means what, I choose this xi minus 1 and xi very close to x naught, so that this product is less than epsilon by 2, let us say this product is less than epsilon by 2, and then choose the other delta in such a way that the remaining part is also less than epsilon by 2. Okay, remaining part is also less than epsilon by 2, then we can again do the same thing. Okay, so what does it mean? That even if a function has one discontinuity, suppose function is bounded, continuous everywhere except at one point, okay, then still it is Riemann integrable, right. Okay, but then one can ask, go further and ask, what is so particular about one point? Okay, suppose it is discontinuous at 2 points, again we can do the same thing, we reduce, for example we can make each, there will be 2 such intervals. Okay, and you can make the contribution by each interval less than, say here we have taken epsilon by 2, look there you take epsilon by 4. Okay, so it does not matter, right. So what it also means is that there is nothing particular about 1 or 2 or anything. If a function is continuous everywhere except at a finite number of points, then it will be Riemann integrable. Okay, but then the natural question is how far we can go in this. Okay, that is, what if it is discontinuous at definitely many points or countable points, countable ways or uncountable points, etc. That is, what is the maximum number of discontinuities that one can allow for a function to be Riemann integrable. Okay, that is an interesting question. Only thing is that question we cannot answer here in this course. Okay, because that requires something which is related to measure theory. Okay, and this is something you will perhaps learn when you learn measure and integration. The answer to that is that function is Riemann integrable if and only if it is continuous, what is called almost everywhere. Okay, it is called continuous almost everywhere. What it means is that if you look at the set of all those points where the function is discontinuous, then that set is what is called a set of measure 0. Okay, that set is what is called a set of measure 0. To understand what is meant by this, you will have to learn what is measure and what is Lebesgue measure, etc. But roughly speaking, what we can say is that set of measure 0 means you can enclose that set by a countable number of open intervals whose total length can be made arbitrarily small. Okay, given any epsilon, you can enclose that set into a union of open intervals such that the sum of the lengths of all those open intervals is less than epsilon. Okay, so that is what is called a set of measure 0. But that result, since I said that results require several other things from measure theory, we shall not discuss that in this course. Okay, I will stop.